Yeah, okay, so welcome everyone. So today it's my pleasure to welcome Bobak Kiani, who will be talking about the hardness of learning and the symmetry. Yeah, thank you, Bobak.
Yeah, thanks for having me. Um, so I guess today I'm going to talk about work which studies how hard it is to learn symmetric neural networks. This goes off of a long line of work that studies complexity theory and learning theory with relations to classes of functions that are given by neural networks. I want this to be a conversation, so I hope people interrupt me throughout and ask questions because I know there's quite a bit here, and if anyone gets lost, I would prefer that you let me know so we can make sure people are on track. So this work is joint with Dean, Hannah, Stephanie, and Melanie. We are people at MIT and Harvard. And I know all of us are happy to chat about this, so feel free to reach out to any of us if you want to chat. Okay, so in this talk, I'm going to discuss how do symmetries help improve learning functions. And most of the results will actually be negative results that show that symmetries often are not enough to guarantee a otherwise hard class of functions to learn is actually provably learnable efficiently. But in the process of doing this, I'll first recap the proper background we need to understand these results, first focusing on fully connected networks or MLPs. And then we'll go into our results, which are for specifically symmetric neural networks. And then I'll talk about some related topics and next steps. So this is the basic setup. We are in a world which often has symmetries. These symmetries are mathematically often placed in this framework of equivariance or invariance. So on the left-hand side, equivariance shows that if I were to apply some group operation, here it's rotation, and I were to take features from this or to take some equivariant map of this object, the features that I obtain should also be rotated if I were to rotate the original input. On the right-hand side, we have invariance. This is, again, you rotate an image. Here it's an image of a digit 3 in MNIST, and that should leave the class of that image invariant. So invariance is a subset of equivariance where we enforce that the outputs are always the same, regardless of what group transformation we apply. And the basic idea is that with enforcing invariance, we have a smaller effective domain. What do I mean by that? Well, our input is often given to a computer as a list of numbers. And if the computer isn't provided with any information about symmetries, it has to learn a function from this arbitrary set of numbers to an output. But if we enforce this invariance property, then just by guarantees of the function class we learn over, we know that the computer won't treat this as an arbitrary set of numbers, but instead as some abstract object that is in a smaller effective domain. And this hopefully results in improved efficiency and sample complexity and things like this. So just for some formalism, here I have this calligraphic F, which is the set of functions we'd like to learn. So you can think of this as the set of image classification objects, for example, or maybe the set of neural networks of a bounded width, something like this. And when we enforce symmetries, we take a subset of these functions. We say that we only want those functions which are invariant. So we have a group G, and we say we will restrict our study to only those functions which are invariant to that group. That is what you see in the bottom. And basic question we ask is, how much does this enforcing this symmetry in our function class actually help us in learning? Clearly, the FG on the bottom there is a smaller set than the F at the top. Again, going back to our other way of writing this, you can think of this as saying if we mod out the inputs to the group, if we take all of our inputs and only look at technically orbits over the group, how much does this help in learning neural networks? And just for some background, this setting covers a wide range of problems that we care about in the real world. So I list some examples here that probably people here, I hope, are familiar with. If not, I can give more details. But for example, images, we know that their symmetry group includes translations. So that's why we use CNNs. Graphs have node and edge permutations. And that's why we have graph neural networks and so on. Okay. So let me just step back. That is the background on symmetries. But for this portion of the talk, I just want to give some related background on hardness of learning neural networks. And actually, what I'll talk about here has nothing to do with symmetries. Instead, this is just going to be some background on some of the key results that are rather historic now, coming often from the 80s, about how hard it is to actually learn a class of neural networks. And then later on, we will tie this back to the symmetries. So the basic mathematical setting we're often concerned with is supervised machine learning, where, I hope people are familiar with this, but you're given a data set. Here we have big N, the data points, and we want to learn a model. We want to find a function by fitting a loss function on those data sets, on that data set. So the hope is that, with supervised learning, we can learn a proper or good enough function with only a finite number of samples. And one possible set of functions that we want to search over is often neural networks. So consider this very simple case. Here I've written the equation for a single hidden layer neural network. You'll note the equation there is just within this sigma, which we'll assume is the ReLU activation, there's an inner product of a bunch of vectors with our input. And then we take a weighted sum over those ReLU activations. And this is just the form of a standard single hidden layer feed-forward network, or a fully connected network, often also called an MLP. And just so that I can't go crazy with this, and we have a setting which we can actually work with, we will assume some regularity assumptions. We'll say that the width of the neural network can't be growing more than linearly with the number of inputs, and the weights have to be bounded in polynomials. They can't be exponentially large. And again, we'll use ReLU activation as well. This is a natural problem setting for various reasons. This simple class of neural networks can be made universal if you take the width arbitrarily large. We believe that even with finite width or a small width, it should be large enough to capture a lot of functions we care about. More practically, I think, understanding learnability of this class of functions can also potentially explain learnability of real-world functions, simply for the reason that, well, neural networks are pretty good at learning real-world functions. So if we can provably learn neural networks, then maybe we can use that proof to show that the real world is also, in some sense, provably learnable. I don't mean to be rigorous here. I just need to give motivation for why we would study this. And stepping outside of just this particular problem, I think this understanding the learnability of neural networks also has implications on other areas, such as the kernel setting, non-convex optimization, representation learning, so on and so forth. So what do we know about this problem? So here I'm going to describe some hardness results that basically state that if you were to give an algorithm that would learn this, well, it would break a lot of beliefs about computer science. We don't believe that such a general algorithm should exist. So probably the first proof of that this fails comes from the 80s. Well, I put the 1992 paper, which is the published date, but this work goes back to the 80s, which basically says there exists a data set of M examples, where if you were to be able to fit this data set to a very particular network, the network only has 3 nodes, and I've shown it on the bottom right there. If you could fit the examples, then you have solved an NP-complete problem. And this is a first instance of how to show some class of functions you want to learn is hard. But this first instance, which is a classic result, is kind of missing some key aspects that we want to make stronger. First is that the problem here is given a specific data set, and we, in general, in the real world, we're not given a very specific data set. We're often given random instances or some data set that comes from some distribution. NP hardness is also a worst case statement. So in learning, we don't want to learn all possible functions. We want to probably learn like with high probability, for example. And fitting the data set is not the only aspect of hardness. We can always potentially add more samples or change our neural network class to go around this issue that is presented here. So more recent results have tried to refine this setting, and they often work in this statistical query model to prove hardness results. Now, I will fully explain this later, but just for now, so I can give you background, think when I say statistical query lower bound or hardness in the statistical query model, think that every gradient will be a step of your algorithm. And each query here corresponds to a step. So I'm going to say there are lower bounds in the number of queries needed to learn a function class. Think each query is a step of your algorithm. So for example, every time you do a gradient descent step in SGD, a query you can think of as asking for the values of the gradient. And again, I will explain this fully later on, but for now, just bear with me. In a few years ago, 4 or 5 years ago, people showed the first SQ lower bounds on learning the function class above. The first one, from my understanding, came from work of Goel, Clivens, and others who said that we proved that any algorithm, any SQ algorithm that is able to learn function class above would need superpolynomial number of queries in the input dimension. This was later strengthened to exponentially large in the input dimension by Diaconiclas, Kane, and others. And these basic results said that for most practical algorithms that we use, unless we put restrictions on this function class above, learning neural networks is likely a very, very hard task, even for IID Gaussian inputs. So here I'm assuming, here the only assumption I make on the input distribution is that each input is an IID Gaussian. Beyond that, we don't have any assumptions. Okay, and then also along that line of work, people also showed that if you were to learn the function class I just wrote of this feed-forward MLPs, this time not of depth 2, but of larger depth, then it is possible, if you were to give an algorithm that were to learn these class of functions, then you would also break some cryptographic schemes that people don't think are breakable. And this is yet another proof that this task in its most general form is very hard. I should say on the other side, there are learning algorithms that learn bounded width neural networks. So when the width k is order 1, for example, there are recent papers that show there are polynomial runtime algorithms that learn these function classes. Okay, I want to step back here and just also comment on one important thing which comes up in this line of work, which is the difference between sample complexity and runtime complexity. And I'm sorry I put a lot of words on this slide, but I think this is important to note. Sample complexity of a problem simply asks how many samples do I need to learn it? And you're given infinite runtime in this setting. And if you've taken a running theory class, you'll have seen things like Rademacher complexity, VC dimension, so on and so forth. These are all statements of sample complexity. And sample complexity is typically polynomial in the input dimension. So if I have a neural network with W parameters, its sample complexity is typically on the order of W. And this is not an exponentially large number in general. And there have been various proofs that enforcing invariance often reduces the sample complexity by a factor of roughly the size of the group. But if something is already polynomial, reducing it by perhaps another polynomial only gives you a smaller polynomial. But in contrast, runtime complexity, where here we ask how much computational runtime is needed, regardless of the number of samples you're given. In fact, in these settings, I can give you as many samples as you'd like, often. Here we ask, how much runtime do you need to learn a function? And this can often be exponential in the number of inputs or in the size of your neural network. And this is an important thing to note because, well, one may hope that with symmetries, you may be able to take this exponential hardness and reduce it to a polynomial. Because as I mentioned earlier, there's already quite a bit of work showing that, well, learning feed-forward neural networks, that even a single hidden layer is already exponentially hard. So here we're going to ask, does enforcing symmetries take this exponential to a polynomial? And again, this is totally different from sample complexity, where it just as a basic point start, it always is going to be a polynomial complexity. Okay. So before I can give our results, I have to give more background again, and I apologize because this will probably be stuff that some people may already know, but I promise I'll get to my results once I give some more background on statistical query hardness. So I mentioned earlier, proofs in the hardness literature have often relied on the statistical query model. And here I'll just give some background for how this model works. In the statistical query framework, we are trying to mimic steps of an algorithm by queries to an oracle. So generally, in practice, we're given a data set, and we perform learning steps by sampling the data set and doing measurements like gradients or loss function measurements, so on and so forth. And we replace these interactions with a data set by queries, and we ask how many queries are needed to learn a function class. So let's just assume for simplicity our inputs are real valued and our outputs a single real number. We have a distribution D of inputs and outputs. To ask our query oracle for a query, we give it two things. We first give it a query function, which is a function that is on the input-output space and has outputs that are bounded. And a tolerance, an error tolerance, that is taking the role of the fact that we have a finite data set. So for example, this you set it to square root 1 over batch size, you'll be recovering something like SGD, where the error corresponds to the batch size error. So once we do this, our query, our oracle, will return a value in the range of the expectation of our query function up to our error tolerance. This may look weird when you first see it, but I will give examples in a second, and I hope it'll become clearer once I give those examples. But just think again that this query function is just something that's going to give us information about the thing we're trying to learn. So here's an example. We can set our query function to be the gradients of a neural network. And for example, I give a gradient of the neural network minus y squared, and this will give us the gradients of MSE, the mean squared error, up to error tau. So this is like mimicking stochastic gradient descent. Similarly, you could set the query equal to some loss function value for a given neural network, and this will return the loss up to an error tau. And if you think about it for a bit, it may not be immediately obvious, but there's a lot of things you can do just by taking these queries. One thing I should say, there is a restricted set of these queries where we call correlational queries, where if the query function only depends on X, then we say that we are a correlational statistical query. And later on, I will give some results which will only be provably true for correlational statistical queries. I should say that this captures almost all algorithms in practice. The only exception that is known in the popular literature is this Gaussian elimination, which requires individual data points. You cannot invert a matrix, for example, by just averaging the elements of the matrix over average queries. That is, I think, the only popular algorithm I know of that falls outside of this framework. So it is relatively broad, and people are still trying to figure out the extent and usefulness of the setting, but so far it's been pretty general in its application. Okay, so our setting now is asking about query complexity. And we will say that a function class is efficiently learnable if any unknown function from the function class can be learned with at most polynomial in the input dimension and 1 over the error number of queries. And if it's exponential in D, then we will say it is not efficiently learnable or superpolynomial. And I will say that I won't have much time to go into the proofs here, but I will just say that in general, I think the proofs here are rather nice because they are often formulaic. And the goal of proofs is to find a subset of functions so that if you take any two distinct functions in that subset, you'll have that their expectation or their average correlation is roughly close to 0. And the intuition behind this is that if you can find n functions that are roughly uncorrelated, they will sort of live in a vector space of dimension n. And if you want to pick out an element in a vector space of dimension n, well, you'll need to take order n queries to do that. And that is the basic idea behind it. So in proving these things, it's often, I think, rather nice because the goal here is to find some way of picking out these functions in this subset so that we know that each is pairwise orthogonal. And this task is often rather formulaic, and there are tricks in the literature to do this, and I think it often makes your life rather easy. And I will say, if you are interested in learning more about the proofs, just feel free to stop me afterwards and ask me questions. I will only give relatively simple proof sketches here, but I promise the actual proofs are not too much more than what I've written here. Okay, so a classic SQ lower bound that I think everyone should be familiar with is the class of parity functions. A parity function is simply a function from ±1 to the d to ±1, so it's a Boolean function. And these functions are, you give me a subset of the elements 1 to n, and you simply take the product of the elements in that subset. This forms a class of functions, and the first proofs of SQ lower bounds basically showed that this class is already exponentially hard to learn. This is, going back to what I said earlier, an instance of something where we do actually know an algorithm to learn it, but neural networks and things that use gradient descent and stuff cannot learn this because to actually learn this in practice, you'd have to do Gaussian elimination, and Gaussian elimination can't be done by doing average queries. So this is a very simple class of functions that is a classic example of what is hard to learn. And note that if you take any two subsets that are not equal, that correspond to two different parity functions, if you take their expectation, their correlation of these two functions, then this expectation will be 0. And this is the basic tool we leverage to prove query lower bounds. Okay, so what if we look at a similar setting for us, and will be the first of our results, where we say we're given random Boolean inputs, and we are told that the function is a Boolean function, so it also outputs ±1, and it is symmetric under some group G. So, for example, you can think of G as permutations. We'll say that it's any function which is, if I permute any of the input bits in any way, it will have the same output value. You can also think of cycles. So if I cycle the inputs, it'll have the same value. These are two examples of possible groups we could have on Boolean inputs. And the action of the group will partition this input space into orbits. So think of an orbit as a set of inputs that I can go from any one input to another by some group operation. So for example, if we had the group being permutations, then you can go from any one input to another input if they have the same Hamming number, so the same number of plus ones in the input. And I'm going to define P naught, which is a vector over the number of orbits. And this vector's, its entry I, will tell us the probability that a random bit string falls in orbit I. So this, again, may be confusing, but as an example, if I go back to my symmetric group or the set of permutations, there's b plus 1 orbits because, well, you can have 0 plus 1s, or you can have up to d plus 1s, and that's d plus 1 possible choices. And the probability distributions are just given by the number of ways to choose how many plus 1s you have in a bit string. And this P naught will end up being correlating to our query complexity in the Boolean case. We can show through a relatively simple proof that any SQ algorithm able to learn symmetric Boolean functions, the classification error small enough, 1/4 suffices. It would require tau squared times the 2 norm of this function, inverse 2 norm of this probability vector number of queries. And this probability vector can, this 2 norm of this probability vector can decay exponentially. So just to give some examples on some possible input spaces you might care about, if we had the symmetric group on n bits, well, query complexity is actually polynomial in this case, partly because there are only order n orbits. But excuse me, if we had graphs, then the query complexity, even under the permutation group, so here it's permutations of nodes in a graph. Here, the query complexity is actually exponential in n squared. Similarly, for the cyclic group, we have query complexity that grows as 2 to the n over n. In this table, I should say I'm assuming the query tolerance is just a constant, so that we can have a query complexity only as a function of x. Okay, so this was for Boolean functions. Let us get to more practical things. I just want to share this Boolean function as a sample of the type of results you might see. And again, please stop me if any questions. I'll assume if there are no questions that I can keep going. So the first setting we look at are graph neural networks. If you haven't seen graph neural networks before, they're a rather broad class of algorithms that are used to study functions which are defined on graphs. Here we have nodes and edges, and we have functions that are permutation invariant. So no matter how I label the nodes of the graph, it, after all, is still the same graph. So I should be able to permute the graph and permute its nodes so that it constructs the same graph, and the function that I use to learn should be invariant to those permutations. And graph neural networks are a broad class of things that are able to do this. So typically in the GNN setting, we have inputs which are node features. So the input x is you could think of it as a matrix of size n by d, n being the number of nodes, and each node having feature dimension d. And you want to learn functions which again are invariant. So one way to do this is in the literature is by message passing. So what happens is if you're given the adjacency matrix of the graph, you'll do a hidden layer. So below I'll write it for one hidden layer. So you'll first do a hidden layer where you take the adjacency matrix and some feature transformation, and you add up the messages or some of the messages from neighboring nodes. And if you look at this hx here, this hidden state is doing one step of message passing. The adjacency matrix is a +1 whenever a neighbor exists for a given node, and it collects this information times some feature transformation, which we aim to learn. And that feature transformation is given by big W. Then we pool all this information in a pooling step. That's what this bolded 1 indicates. It's just a average pooling. And we then just apply a single linear transformation to get a single output number, real value output number. And although it may not be immediately obvious, you can see here that if I were to permute the adjacency matrix and the nodes, this transformation would be invariant to those permutations. So in what follows, I'm going to ask how hard it is to learn the function class given by this, well, relatively simple form. So one setting we can consider is where we have a Erdos random graphs. Here, the inputs are all just a random graph where each edge appears with probability p. And each edge appears with probability independent of other edges. So take any adjacency matrix, and for any entry, you set it to +1 with probability p, and you set it to 0 with probability 1 minus p. And we will say that our hard functions, the set of GNNs that are hard to learn, they're going to look like parity functions. So the way we'll do this is as follows, and this may take a little bit of time to describe, but in the end, I hope you'll see that it looks very similar to the parity functions that I described. So what we'll do is we'll say, given an input graph A, we'll define this vector CA, whose ith entry counts number of nodes with that number of outgoing edges, with I minus 1 outgoing edges. So our target function, or a set of neural networks that we'll show is hard to learn, are going to be functions of this CA. And what I write below is that the CA gives a Boolean vector, or we can treat the CA can be treated as some sort of Boolean vector in a way where we just sum up all the possible values of CA in some given subset, and we just take it mod 2. And this will resemble in a way the parity functions we showed earlier, which are hard to learn in the SQ model. And well, I don't show the proof here, but it's not too hard to see that this can be constructed with a single hidden layer graph neural network of the form of this prior slide. Why is that? Well, counting how many nodes that have I minus 1 outgoing edges is a linear transformation. Is a piecewise linear transformation, which can be made by a bunch of ReLUs. And then the second step is just also another piecewise linear transformation, which we can do in the second layer. Okay. And our basic result shows that this class of functions here, indexed by the subsets, is exponentially hard to learn in the number of nodes. So already we have a exponentially hard class of functions to learn for this single hidden layer GNN. And the proof here follows very similarly to the classic proof by Kierns and et al., where we use the fact that these resemble parity functions and these are orthogonal with high probability. So moving on from graphs, we also look at symmetrized neural networks. Here we take this frame averaging view, which covers a lot of different types of networks, including deep sets and convolutional neural networks and point cloud networks and so on. And if you haven't seen this before, it's, well, a relatively simple idea. And let me just explain it. It can be confusing the first time you see it. So here we take a set of functions h, which are not symmetric. These can be arbitrary functions. And then we symmetrize these by averaging them over a frame. So just to give a couple examples, you can think of the frame being a sort. So if you take a set of inputs and you first sort them, if you pass it to any arbitrary function afterwards, it's going to be invariant, because as long as you first sort the inputs, it's going to make sure that no matter what input you give it, if I were to permute it, the sorting would make sure that I undo the permutation, and I would pass it to a function. And no matter what that function is, it's going to be invariant permutation. Similarly, you can also just average the function over all possible group transformations. This gives what's called the Reynolds operator, and this is another way to construct a frame which gives you a invariant function. And in general, any frame takes the form as follows. It is a function which takes an input and outputs a subset of the group. So in the sorting example, you take an input and you output the permutation which sorts the input. In the group averaging case, you would take any input and just output the whole group. The frame would always be the whole group. And then you average the function h over the frame that's given. And what I'll say in what follows is going to hold true for all possible frames that can be written in this form with some caveats, which I'll describe. Okay, so as mentioned earlier, the basic idea here is we want to start from some hard-to-learn function class f, which is not invariant, and then we'll symmetrize them by taking averages over the group. Here I'm taking the Reynolds operator, but I'll discuss later on what happens when we discuss frame average networks. And symmetrizing these functions reduces the size of the function class by a factor size of the group. So it's not too hard to see that, well, at most, the best we can hope for is a factor of the size of the group reduction in the hardness. And just by this fact, it's, well, you'd have to prove it, but it's not too hard to do to show that single convolutional neural networks, which are instances of symmetrized, fully connected networks, these are hard to learn by just taking the hardness results I mentioned earlier for fully connected networks. And since the cyclic group, or the group of translations, is at most size of the input dimension, there's only, if you have an n by n image, there's only n squared possible translations you can do. So if you take an exponentially large number and divide it by polynomial in n, it's still going to be exponentially large. And here's our formal proof, or here's our formal statement, which there are some caveats which I haven't added in here, but if you want, we can chat after and talk more about them. But we basically show that any CSQ algorithm, this C here means correlational, which I mentioned earlier, any correlational statistical query algorithm able to learn the class of frame average networks up to constant error requires a superpolynomial number of queries divided by the largest orbit size of the frame. So if this largest orbit size, as in the CNN case, is polynomial in n, it won't change the fact that we have a superpolynomial hardness result. And this proof is actually just follows from taking the hard function classes that I mentioned earlier for feed-forward networks. And we show that frame averaging just preserves this hardness. In fact, you can write out the specific functions that are hard to learn, and I wrote them in the bottom. It is not it may take some time to stare at it to actually understand what's going on, but the nice thing here is that you can literally say these are class of functions that are really hard for neural networks to learn, and you can write out the explicit form of them. And the ones we show are hard to learn in the group average case are simply frame average versions of these already hard functions. So since we have functions that we know are hard to learn, we can actually run experiments, and we try to learn these functions by looking at overparameterized GNNs and CNNs. So here we take the hard functions that I wrote earlier, the GNN1 and the CNN1 are shown in this example. And we look at over-parameterized GNNs and CNNs of the same form. So I take, the target graph neural network or the target convolutional neural network, and I add more parameters that it potentially is easier for it to learn. And what you can see is that the training gets stuck. So on the left-hand side, it gets stuck because it can't fit the data set. And the right-hand side, where I give it, sorry, on the right-hand side, you see it gets stuck by it can't generalize, and on the left-hand side, it just can't fit the data set. And we, in the paper, tried other types of experiments with different network sizes, different target functions, different optimizers, so on and so forth. And everything we tried, it failed to learn class of functions we described. So here are just a summary of our formal hardness results. We give various different hardness results for different function classes. And I won't go through all of this in detail, but again, if you'd like to chat more about these or ask more questions about how we got these results or next steps, just grab me after the talk. Okay, so I guess let me just step back and discuss open questions and other topics. I will say that I think there's a lot of work, in my opinion, that can still be done in this area. Our results kind of point to the fact that symmetries are not enough to give provable learning guarantees, and something else must be added. And to me, the natural question, of course, then is what else needs to be added? What other restrictions need to be made? So on and so forth to give provable learning guarantees. So first thing is understanding where hardness arises. And my belief, and I think other people also probably believe this, is that the hardness likely arises from edge cases with unusual weights. What do I mean by this? Well, in the real world, learning with convolutional neural networks, graph neural networks, so on and so forth, works pretty well. And if we want to give provable guarantees, they have to avoid the hard instances that we show here. And what I think, and I think probably is true, is that the hard instances are likely coming from edge cases, things that are weird functions that jump around a lot, like parities, for example. So what are ways to get around these edge cases? Recent work has looked at random weights, so I'm not allowed to choose the weights of the neural network myself. I have to learn a random neural network where the weights are given by, for example, Xavier initialization. And recent results do give some learning algorithms for this. You can also bound the number of channels. So if you remember back in the section on learning feed-forward networks, I stated some recent results that showed that networks of bounded width bounded by constant are efficient to learn. And perhaps in this setting, we can also give proofs that bounded number of channels is also efficient to learn. We should say also that in the CNN case and also in GNNs and so on and so forth, there's potentially restrictions on locality or the size of filters. When we use a CNN, our filters are often like 7 by 7 or 3 by 3 or 5 by 5. And this restriction, limits some of the hard functions that I wrote earlier. And perhaps adding this locality in can make things provably learnable. And there is some work on this in this regard. I give some references here, but so far, in my opinion, none of them have really given something satisfactory, and they require assumptions that are perhaps too strong. I should say that it would also, in my opinion, be interesting to look at hardness results in other models. So for example, I mentioned cryptographic hardness results, where if you were to learn the neural network class, then you would be able to solve some cryptographic scheme, which people don't believe we can break. So these results are probably stronger than SQ results because they don't require introduction of some oracle. So this Daniele-Vardi work is the classic work in this regard. And potentially, I think you can use those works. Sorry, I see a comment in the chat. Oh, yeah, thanks for coming. And then I also want to say that in the graph case, there's been some work showing in the statistical literature which show hardness results by studying the landscape of optimization and showing this overlap gap property, which basically says that local minima are very clustered, and it's hard to pick the right cluster. But more generally, stepping outside of proof techniques, I just think in general, we should aim to understand what properties the real world make problems provably learnable. Because I think shedding light on that answer really will help us understand why deep learning works. And thank you guys for listening to my talk. That's all the information I have.
Yeah, thank you very much. Thank you. Any questions or comments?
I have a question. How do you see the orbits coming in, and how do you compute? How do they actually get involved into the estimates?
Okay, so in this case, in the Boolean case, it's pretty directly. So let me just go to the example here. So for this example, the symmetric group, you have d plus 1 orbits, and the probabilities are equal to these d choose k values divided by 2 to the d. And the probability vector of this gives you the query complexity. So in general, if you're going to have, let's say, n orbits, this probability vector will decay roughly with the number of orbits. In fact, you have this bound here, which I don't show the proof of, but it's if you just do Holder's inequality on this norm, you'll get this bound here. That on this norm of the probability vector. So basically, the query complexity will scale with the number of orbits. In general, for these graph neural networks and stuff, it's harder to say that it correlates to the number of orbits because we are really restricting the function class itself. Message passing is not able to represent any possible function on graphs. And so I don't have a great intuition there in terms of the number of orbits, but just by looking at this function class, we are able to find enough things that are orthogonal to give us exponential SQ dimension. I hope that helps.
Yeah, so your result is also providing a lower bound, or just the upper bound?
We only have hardness results in this work. So we only say that you need at least this many queries to learn. If you give an algorithm to learn, then you also give an upper bound, but we don't have any in this.
Okay. Yeah, thank you.
Yeah. Someone raised their hand, Reagan.
Yeah. Yes, I have a question.
Yeah.
On page 19, where you define the complexity.
Yeah.
So yeah. So I was trying to understand, because you say just for a neural network, and reading the paper of Baron, and he showed that the neural network should be of a specific type, like of Baron class, or with satisfying the Vapnichev-Rokis conditions. And in that condition, the error will not depend on the input data. And for the complexity, I don't see the input data appearing. And since you are using just neural network, but we know, like, if you're just using neural network, the case of dimensionality should be there. So what can you say about this?
So, okay, so great. So VC dimension is a statement of sample complexity. And in the pack learning model, which I think is what you're referencing, but correct me if I'm misunderstanding, but there when we say something is efficiently pack learnable, we're asking how many samples we need to learn for any distribution of the data. So you give a parametric class of models, say neural networks, and you say for any distribution, how many samples do I need to learn? But this type of VC dimension results do not apply to runtime complexity. Here, in fact, I'm saying you can have as many samples as you want. I simply want to ask you how much runtime do you need to learn a function class. And I apologize, I've been a little vague here with the input distribution. So you can look at two different settings. You can look at one where the input distribution is given, or one where you have to give an algorithm for any input distribution. But for the results we look at specific input distributions, which are relatively natural, like random graphs or IID Gaussian inputs. And we show that computational runtime needed is exponential for that class of functions.
Okay, thanks a lot.
Yeah.
All right, good. Any other questions or comments? All right, seems not. Yeah, thank you again, Bobak, for the talk, and then thanks everyone for coming, and see you soon. Then, yeah, thank you.
Thank you. Appreciate it.